Good morning, good evening, or good afternoon, depending on where you're joining us from today, and thanks for attending today's Azure Cosmos DB technical training session, technical overview of Azure Cosmos DB. I'd like to briefly go over a couple of housekeeping items before we get started. On the left-hand side of your webinar console, you should see a Q&A box. Please enter any content or technical questions you may have in the window, and we will address them as they come in. This webinar is being recorded, and you'll be sent a recording of this presentation within 48 hours at the email address you registered with. We've also provided a couple of resources on the right-hand side of your console that we think you may find helpful. I'd now like to introduce today's speaker, Andrew Liu.
Hey, my name is Andrew Liu. I'm a program manager on the Azure Cosmos DB team. I've been working on the team since our initial preview launch many years ago, and it's been a wonderful journey ever since. Today I'm going to make the assumption that you've at least heard of Azure Cosmos DB, and this is intended to be a technical overview. I'll be giving you a crash course on the Azure Cosmos DB resource model, talking a little bit about some of the core concepts like request units, what are they, partitioning, how you choose a good partitioning key, and global distribution, how you both set it up as well as choose the right consistency model for your application. I'm not going to go into a long overview of what Cosmos DB is. Instead, this is going to be more of a technical crash course. But to get everyone on the same page, what I'll do is I'll give you a quick 1 minute what is this thing, just in case you haven't heard of it. At a very, very core of what Azure Cosmos DB is a globally distributed multi-model database service. At a core, it actually does three things very, very well. Those three things are partitioning, replication, and resource governance. The replication allows us to build turnkey global distribution capabilities, which we augment with a well-defined set of consistency models that you can tune the consistency versus performance for your application. The partitioning allows us to elastically scale out your application and database's storage and throughput. And the resource governance allows us to bring a unique set of capabilities in which not only is this a fully managed database service, but we're actually the first and only database to offer SLAs around performance characteristics like throughput, latency, and consistency. On top of this core platform, we're able to represent multiple different data models very efficiently out of it, and these are the key value column family, document, and graph data models. On top of these data models, we expose them through a variety of different APIs, including a SQL, MongoDB, Table, Gremlin, JavaScript, and Cassandra API. So with that said, now that you have an idea of what is this thing, let's actually start taking a look at the resource model so that you have the overall context for understanding how you can build an application on top of this database service. At a very, very high level, the very first thing that you're going to encounter is an account. The account is a set of URI and key for you to connect your application to the database service. To provision an account, it's very easy. Everything starts with the Azure portal. You can access the portal at portal.azure.com. And here I have just a little screenshot. What you do is you end up clicking New, Databases, Azure Cosmos DB. I give that a name, and that'll be the URI that I connect to. Under API, I have all of the different APIs available for me to choose from. I can tie that to an existing Azure subscription, place that in a resource group for organization, and choose a starting location on where my very first region will be. From here, I click Create, and I'll have an account in roughly 3 minutes. You're not going to be spending a day configuring software, installing software. 3 minutes, and your account is up and running. From here, once your account is provisioned, the next resource deeper into the hierarchy is a database. Within a database, this is actually just a logical grouping of both containers and users. The users and permissions allow you to do fine-grained access control over the containers and items, and otherwise the databases is just a logical grouping. Containers are where things get interesting. Because this is a multi-model database, a container can actually be projected into several different kind of things. If you're using a document-oriented data model, let's say through the SQL API, we call this container a collection. Whereas if you're coming in through the Graph API and running Gremlin queries, we'll call this container a graph. And if you're coming in through the Tables API, we'll call this a table. Within that container, where things get interesting is this is where physical resources start coming into play. The very first thing you do is, of course, you name the container. But this is where storage and compute actually come into play. And compute will be measured in request units per second. I'll talk a little bit about that in just a minute. But the gist here is you can think of this as the CPU, memory, and I/O for running the compute for, well, all of the fancy things that a database does in terms of indexing and query. Once you've provisioned a set amount of starting compute units, which you can scale up and down at any time, we'll also ask you for a partition key. This is going to be a very, very important concept in Cosmos DB. And if there's nothing else you take away from this talk, please pay attention when we get into the partitioning side of the story. This is the top-level design decision you're going to make when you create a Cosmos DB collection, as well as this is going to basically have huge ramifications for the success of your project moving forward. Basically, this is how we're going to both distribute your data onto underlying storage partitions, as well as how we route those requests efficiently. Once you have created a container, you can store your actual items or records. And of course, depending on the different data model, we'll call these different things. If it's a document-oriented data model, this item happens to be a document, whereas if this is a graph data model, this happens to be a set of vertices and edges. In addition to supporting the actual records themselves, Cosmos DB does have a server-side programmability API. It's exposed as a JavaScript API, which is a subset under the SQL API. This will take form in the form of store procedures, triggers, and user-defined functions. And for store procedures and triggers, these are going to be your primary mechanisms for performing multi-record transactions. Unlike a lot of other distributed databases, Cosmos DB does bring multi-record transactions back to the table. And for store procedures and triggers, what this will look like is shipping a body of business logic. We use JavaScript as a modern-day T-SQL. And all of the operations, CRUD operations that are performed within that business logic will be atomically committed in an all-or-none fashion. The user-defined functions are a little bit different. They are a way of representing a body of business logic for augmenting our query language. And so you can write projections, filters through a custom user-defined function to implement custom business logic on top of that. Lastly, in our resource model is this concept called a conflict. 99.999% of the time, you'll never have to interact with conflicts, but you should be aware that they exist. The reason why they exist is because this is a distributed database. And what that means is that we'll be replicating your data both within a data center as well as across multiple regions should you choose to set up a multi-region configuration. Now, one of the things that every database or any kind of storage product has to obey is the laws of physics. At the end of the day, a packet over a network cannot travel any faster than the speed of light. And so if you have multiple data centers configured around the world, it takes in the order of potentially tens or hundreds of milliseconds to replicate data from one region to another region. We guarantee as a service the durability of all data stored in Cosmos DB. And what that means is that when you write data to one replica, we'll propagate to all replica, and we'll durably commit onto those SSDs. Now, here's the thing. What happens if a failover has to occur? Let's say whether that's due to a natural disaster like a hurricane or a geopolitical incident, let's say, I don't know, World War III breaks out. Hopefully that never happens, but the thing that we can help you with is at least make sure that your data is safe. And what we do is when a region goes offline, data that is in flight, that is still being propagated, when that network link is severed, we have durably saved all of that data onto disks. And when that original region comes back online, what we can do is we can make sure that we try to bring that back into the global replica set. When that happens, there's a potential for conflict. Let's say your application is writing to region number 1, and we have to trigger an automatic failover to region number 2. For resiliency, what ends up happening is the application detects that and rewrites those records to region number 2 and updates them. If region 1 were to come back online, it turns out you now have 2 sources of truth. And what we'll do is all of the records that have a conflict in region 1 when we bring online will be surfaced through this conflict feed. This is an edge case scenario, but do know that it exists. We do safeguard and guarantee the durability of data. Now that you have a user view of the resource model for Cosmos DB, let's also talk a little bit about what happens behind the scenes. Cosmos DB is a massively distributed database. At a high level, the way I view the world, and my engineering team views the world, is we start with planet Earth. Planet Earth has an ever-growing number of Azure regions. At this point, I've lost count. I think we're beyond 30 at this point. Each of these Azure regions, well, they're composed of data centers. At the end of the day, someone has to actually buy the real estate, buy the power, the infrastructure, and, well, put in computers. These data centers are composed of stamps. Think of these stamps as server racks. We organize these stamps into fault domains, and you can think of a fault domain as a unit that has a shared set of hardware. So think of a server rack that has a shared, let's say, network switch. We deploy these massive clusters of hundreds of machines over tens of fault domains, and each of these clusters are composed of machines that run these little containers. This is where the magic happens. Within these containers, we have replicas, and really the replica is the core building block in Cosmos DB. The replica has the resource governance for guaranteeing performance and doing admission control. It has a transport layer for doing replication across replicas, and it hosts the actual database engine where all of the query, indexing, etc., the database logic is hosted. What we'll do is each time you provision a container, a Cosmos DB container, a user container, like a collection, what will happen is we'll actually have a container that's composed of partition sets, and each of those partition sets is composed of replicas. We'll actually talk a little bit more on partitioning in just a minute. But before we do, I want to cover a very, very important concept, and that's request units. A request unit is a logical abstraction over all of the physical resources it takes to perform a database request. Think of this as the CPU, the memory, the I/O. And what we do is we actually rate limit the requests coming into the database at a request level to guarantee performance isolation while having very, very low total cost of ownership. Basically, because we're able to implement resource governance in the software stack rather than relying on a operating system on an underlying VM, what that means is that we can dramatically raise the utilization on our clusters, reducing our service costs, and therefore passing on those service costs to you, to the consumer, and that you can have a distributed database at a very, very low price point. You know, it doesn't cost you millions of dollars. Instead, we can start a distributed database at tens of dollars. Now, the reason why we use request units and not requests is because, well, not every request is the same. If you do a database read versus a database, let's say a document create, when you read a document, we can actually go to a single replica depending on the consistency level and immediately return that copy of data. And for that reason, we baseline a request unit to be a single read on a 1 kilobyte record. We find that 1 kilobyte is the typical record size. For writes, what we'll have to do is we'll have to at least replicate to a quorum of replicas in that local data center, as well as generate index entries. So a typical write on a 1 kilobyte record is about 5 request units. And of course, we support replace operations where we'll actually compute the delta and pass on the savings for you, as well as we support a rich query layer in which the charge of a query is roughly proportional to the number of query results, basically the amount of I/O that the underlying system has to do. Now, the intent of request units is actually to make life easy for the user for capacity planning. Let me give you an example. Let's say I'm back in the on-prem world, and when I'm building an on-prem database, what ends up happening is I buy a machine that has CPU, memory, and I/O. It has 3 different dimensions. And let's say in a real-world scenario, I want to scale my application from 1,000 requests per second to 10,000 concurrent requests per second. How much RAM do you buy? How much CPU do you buy? Do you know if RAM is even the bottleneck? Well, what you might do is you might do some stress testing and find that RAM is indeed the bottleneck today, but you don't know how many gigabytes of RAM translates to how many requests per second. Furthermore, the moment you add some RAM, CPU becomes a bottleneck, and then as you add some cores, I/O might become the new bottleneck. It gives you a very, very hard set of dimensions to scale against. This is what request units is intended to solve. What we do is we use a machine learning model to give you a predictable RU charge on each operation. So if you do a create document request on a given document, and we say that this is 5 request units, well, you can actually feel rest assured that this request will cost you 5 request units today, tomorrow, and the day after. It won't actually ever increase. And we use a logical charge to actually get rid of all the noise around things like garbage collection and other kind of background processes. This allows you to do capacity forecasting in a basic you can do mental math over this. So in that example I mentioned, scaling from 1,000 operations per second to 10,000 operations per second, if you know that these are write operations and your typical write is about 5 request units, the math is simple. 1,000 requests per second multiply 5 request units per request equals 5,000 request units per second. That's how much compute you would have to provision. And to scale this to 10,000 request units per second, doing 10,000 request units, 10,000 requests per second times 5 request units per request is 50,000 request units per second. So literally, I can actually give you over 30 seconds some mental math and tell you exactly what you need to scale off of only one single easy dimension. What we do is we rate govern or rate limit your request based off of the amount of provision request units, and we actually guarantee performance. So when you set aside and provision, let's say 10,000 request units per second, we set those system resources aside for you, and we guarantee that any given second, that is your scalability target, we can deliver that amount of throughput. We've set those resources aside for you. And you can think of this as a token bag system. Every time you perform a request, we'll take some request units out of this token bag, and each second we'll also add request units back into this token bag. As long as that you have a positive number of request units, we'll allow these requests to go through. If you ever empty the bag to 0, or we actually allow it to go into debt slightly, if it goes into a negative number, what we'll do is we'll rate limit the request, what's called a database throttle, and our client SDKs are actually smart enough to retry. Basically, you've used up all of your request units, and the database will inform the client, hey, hold on, you've used up all of your RUs. Wait a second, retry, and the request will go through. Now, we allow you to scale these RUs up and down on demand, and we also bill hourly. And what that means is that you can actually use this to only provision the amount of RUs you actually need. You don't actually need to plan for your peak year-round as if you were investing in buying a on-premise cluster. The nice thing about this is if you have a workload, let's say that is hot from hours 9 to 5, you can scale up your RUs from hours 9 to 5 and scale down on your after hours when your database is cold, so that you're not actually paying for resources that you don't need. This is one of the really awesome advantages of using the cloud. You're only paying for what you need. At the high level, from an operational standpoint, in terms of what you want to monitor on a database, request units is actually the top level, most important metric for you to monitor. as a result. And what we do is we actually also have a set of background tasks for optimization where we can set data retention policies to purge records over a certain date, as well as do index transformations using any kind of leftover RUs you have on the system. Now that you have a basic idea of request units, let's also start diving into partitioning. So as we know, a container, so for example, a collection, can scale from just a couple request units per second to millions of request units per second. It can also scale from just holding a gigabyte of data to many, many petabytes of data. So how is this actually made possible? And the way our topology works is, well, a container actually contains many, many underlying partition sets. And what we do is we distribute that data across the underlying partition sets as well as route requests efficiently to those underlying partition sets. If you've ever sharded a database before, you know these concepts as sharding and partitioning. Now, if you take away just one thing from this webinar, please pay attention to this section. Because choosing a good partition key is the #1 key most decision that you're going to make in Cosmos DB as you design out your solution. And what I'd like to do is demystify what actually happens underneath the hood, as well as give you a set of guidelines so that you choose a appropriate partition key for your solution. So let's start with an example. Let's say I have a workload that scales with the number of users. As the number of users grows, I'm going to have more storage requirements. I'm going to have higher throughput requirements in terms of how many concurrent requests per second are running against the database. Let's say that's my example. And I find that I also tend to scope my queries and transactions on a user, and so therefore I've chosen user ID as my partition key. The important thing to know here is that partition keys are a logical partitioning abstraction. Each partition key you can think of as a logical partition. What we do behind the scenes is a technique called consistent hashing. And for consistent hashing, the first thing what we'll do is we'll be hashing those partition key values. And if you were to think about all of the potential hashed values, starting from, let's say, 000 all the way to max value, you can think of I have a very, very broad range of values that the user ID can hash to. By hashing the user ID, or the partition key here, I can get a nice pseudo-random distribution to avoid any kind of hotspots from load balancing these partition keys. So for example, if I have a sequential partition key where the user ID goes from 0, 1, 2, 3, 4, 5, you don't want all of them to actually land on the very first partition. You want them load balanced across many partitions so that you're utilizing the system efficiently. Now, what we're going to do is the system in the background is actually going to start calculating how many physical partition sets are actually required here. This is going to be based off of the actual dimensions around storage and throughput. And this is actually an implementation detail, because at the end of the day, what you really care about is how much data can I store and how many concurrent requests can I actually perform against the database. The number of actual physical partitions really does not matter. It's an implementation detail that basically, the only reason why you might care is maybe for ego. I mean, at the end of the day, maybe there's some sense of pride on, wow, what a large cluster I have. But from an actual business value standpoint, this is just an implementation detail. Now, what we do is if we calculate the number of physical partition sets behind the scenes, what the service will do for you is, let's say for sake of example, you require at least 4 partitions to satisfy your storage requirements, at least 3 partitions to satisfy your throughput requirements. Then therefore, the service knows that by provisioning at least 4 physical partition sets, it can guarantee that there is neither a bottleneck on storage or throughput. Furthermore, let's say you have billions of users using your platform. Let's say you're a social network and your user population is planet Earth. Well, that means that we don't have to provision a billion physical partition sets. That would be a very high-cost solution. what we can do is we can co-locate those logical partitions on these physical partition sets to dramatically reduce the cost footprint of the solution. So in this example, let's say I have 4 physical partition sets. What will happen behind the scenes is for the first 25% of the partition keys, what we'll do is we'll map them to that first physical partition set. The next quarter of logical partition keys will map to the next physical partition, and so forth. We call these partition key ranges. So it's a range of partition keys based off of the hashed value. Why do we do this? Why do we use consistent hashing? Well, it turns out this is actually a standard, and for a very, very good reason. It is a very good means of building elasticity into the system. So, for example, what happens if this partition needs to grow? Let's say, I'm going to just pull some numbers out of thin air. Let's say partition keys 750,000 to 1 million. For that range of partition keys, what you're finding is we're at 80% of storage utilized. How do we make more storage? Well, rather than backing that range of partition key values with 1 partition, we can simply back that with 2 partitions. So what we can do is we can subdivide that range of partition key values into half and half, where half of those values will go to child number 1, half of those will go to child number 2. And now suddenly you have double the amount of storage as well as double the amount of throughput capacity. The really, really nice thing about this is, number 1, for consistent hashing, we don't have to do any kind of rebalancing or reshuffling across any of the other partitions. We can do this silently in the background based off of a threshold value, and we do this automatically for you. And this is one of the big value adds of Cosmos DB. For building a large solution at scale that requires partitioning and sharding, you don't have to worry about managing the partitions. We will take care of that work for you. We will do this as a background task, and we will guarantee availability during this background operation, and then silently swap that parent for 2 child partitions as needed. You don't have to lift a finger. So Cosmos DB does basically 99% of the work involved in partitioning. Really the hardest problems is this elasticity as well as the routing the requests. But at the end of the day, you still have to put in 1% of that effort. And specifically, that is choosing a good partition key. So let's talk about some of the design goals that you need here. Number 1, you want to choose a partition key that with the goal of distributing your overall request and storage volume. You want to avoid hot partitions. And I'll give an example of a bad partition key. Let's say I have an IoT telemetry store where I'm constantly having many, many devices write into the database, and therefore it's a write-heavy workload. And let's say I chose a partition key that is current time. Well, what will happen is at any given time, at any point in time, all of the requests coming in will have the exact same partition key value, which is the current time. And so therefore, all of those requests will land to 1 partition as opposed to getting load balanced across all of the underlying partitions, leaving 1 partition blazing hot with all of the other sibling partitions just left idling. That's not a scalable way of building a solution. You want to choose a partition key that effectively load balances your requests at any given time. And so for that IoT device telemetry scenario, perhaps a better partition key might be the device ID, since the chances are the amount of requests will increase as the number of devices are deployed. Now, I don't want to mislead you in saying time is not a good choice of partition key, because it might actually form a very, very good composite key with device ID for increasing the cardinality. And what you actually want to do is you want to choose the partition key based off of your actual data access patterns. Let's talk about the second design goal before we give you a set of steps in terms of how you're going to evaluate this. The second design goal that you want to have is you want to choose a partition key that allows you to efficiently route queries, at least for any kind of highly concurrent query, as well as you want to choose a partition key that allows you to easily leverage the store procedure and trigger functionality for transactions. Basically, we scope multi-record transactions at a partition key level. That's number 1. And number 2, for efficient query routing, let me give you an example. Let's say I go back to my previous example where I've partitioned a container by the user ID. If I run a query that says something like select star from this collection where user ID equals Andrew, our SDKs are intelligent. They'll actually parse the query, see that the partition key is Andrew, hash Andrew into a value, let's say 123, and understand that the topology when the SDK boot up and downloaded the topology of the partitions, it knows that 123 is on partition 5. And so that SDK will automatically route that query to partition number 5. Now, in the absence of a partition key, we'll perform what's called a fan-out. And an example of this is, let's say I run a query now in that same collection, partition on user ID, where I omit the partition key in the where clause or the filter. So I do something like select star from this collection where birthday is October 20th. Well, what will happen is all of the underlying partitions may or may not have relevant data, and what we need to do is guarantee query correctness. And so we're going to fan out the request and we're going to ask every one of these underlying partitions. This is going to have some impact here. And you'll want to understand what is the impact. From a latency standpoint, you're actually okay, because what can happen is we can fan out to all of these underlying partitions in parallel and return the aggregated results. However, you are using a minimal amount of compute resources on all of the underlying partitions. So if this is a query that you're fanning out, 1 or 2 times per second, or even 100 times per second, okay, that's fine. It's minimal load on each of the underlying partitions. However, if this is a query that needs to run, let's say, 10,000 times per second, well, now you're going to actually start exhausting the throughput on all of the underlying partitions, and this becomes an unscalable solution. And so at least for the very bulk of your queries, you want to make sure that they can be efficiently routed and do not have to blindly fan out to every partition. So here are the steps that you're going to want to follow for choosing a good partition key. First, you're going to ballpark your overall scale needs, and this is going to be in terms of the amount of size or storage. So is it gigabytes? Is it petabytes? You're also going to ballpark the scale needs in terms of throughput. Do I need, 1 request per second, or maybe 100 requests per day, which will translate to, a fraction of a request per second, or do I need millions of requests per second? The reason why you're going to ballpark this is you want to get an idea of how much do you actually care about fan out. If this is a small solution and you're going to fan out, your fan outs only touch a single partition set, you know what? In that case, I don't really care about fan out. Whereas if this is petabytes of data, the overhead for fanning out a query becomes a bit more expensive. Number 2, you're going to want to understand that workload. And specifically, the first thing you want to do is you want to get an idea of the ratio of reads to writes. A ballpark of how many reads per second, a ballpark of how many writes per second. You do not need to be precise. You don't care if it's 101 reads per second versus 102 reads per second. That doesn't make an impact, but you do want to get an order of magnitude. So the difference between 10 requests per second versus 100 versus 10,000 does make a material difference. Once you get an idea of the ratio of reads to writes, you actually want to start drilling down. For reads, for best practice, what you want to do is you want to start writing a pseudo query of maybe your top 3 or top 5 queries and take a look at that where clause. If you see the same thing pop up over and over in the filter for your where clause, let's say your top 3 queries all filter on user ID, and you find that this is a read-heavy workload, well, my instinct here will be user ID might be a good candidate for a partition key. For writes, what you want to do is understand the transactional needs, because multi-record transactions are scoped to a single partition key value, at least for stored procedures and triggers. To do distributed transactions, you'll have to implement client-side logic. And so to avoid that, you want to actually try to encapsulate that transactional scope with your choice of partition key. While you're doing this exercise, you might also want to think about your ratio of inserts versus updates. I bring this up because you're already actually taking a pretty good set of steps for evaluating the partition key. The ratio of inserts versus updates has less to do with the partition key choice and more to do with the object model on whether you want to collocate data within, let's say, a denormalized single record versus multiple records. which is another story. But because you're performing this set of steps, it's a good thing for you to actually take a look at and also factor in terms of the overall design of your database, your data tier. One thing I can't stress enough, I get a lot of questions in which, let's say you're partitioning off of user ID and it's a massive scale social application. Let's say you're building, I don't know, the next Facebook or Snapchat in the world. What ends up happening is you might have billions of partition keys, and people sometimes worry, well, if I have billions of partition key values, am I going to run into problems? The answer is no. In fact, the more partition key values you have, the better your scalability targets are. And at the end of the day, the number of physical partition sets is bounded by the number of logical partition keys that you define. So if you have a total of 1 partition key value, well, we can at most distribute this across 1 underlying physical partition because we guarantee that we collocate that logical partition across no more than 1 physical partition. But because we can collocate many logical partitions on a physical partition, the nice thing is even if you have billions of partition key values, we can collocate this on a small number of physical partition sets, let's say starting with 1, and then we can always grow that to an ever-increasing number of physical partition sets, such that if you have billions of keys, then we can grow this to billions of physical partition sets. Basically, the number or the cardinality of your logical partition key is the scalability bounds for how much Cosmos DB can scale out your database. So we've covered at a high level the resource model, how resource governance comes into play, how partitioning works underneath the hood. Now let's talk about the third aspect of a distributed system, that's replication. Why you care about global distribution? Number one is the obvious one. It's high availability. And so let's say you want you have a mission critical application which you do not want your business to go down just because a hurricane is disrupting network connectivity or power infrastructure in a certain region of the world. You want your application to be highly resilient to any kind of natural or geopolitical disaster. Well, one way of doing this is you set up replicas across the world, but there's actually a more interesting scenario here to discuss. And this is made possible by 2 things. Number one is we have a write-optimized database. Number 2 is we have a tunable consistency model to give you read predictability. Basically, you cannot cheat the speed of light. You cannot send information faster than the speed of light. If you figure out how to do this, please talk to me because you have done something amazing here. But assuming you obey the laws of physics here, and we are bounded by the speed of light, then how do you actually serve a global user base, an application that has users spread all around the world, and do so with very, very low latency? And so imagine I have a database that lives in, let's say, California, US. So that's the west side of the US for those of you outside of the US. And I have users connecting from Indonesia. Well, it turns out that sending a packet halfway around the world incurs quite a bit of latency. You're probably looking at a couple hundred millisecond latency. And if I want to do any kind of real-time scenario, I need sub 10 millisecond latency. So how do I actually achieve that? Well, turns out we've been doing this for decades with CDNs, right? For static content, what we do is we exploit data locality and bring the data closer to the user so that when the user is ready to make a request, it's actually being served out of a local region, a local data center, as opposed to having to ship packets all around the world. Well, for a long time, CDNs have only solved this for static content because they rely on a high degree of caching and do not bring consistency for a write-heavy scenario. This is a problem that Cosmos DB has solved. As a database, as a write-optimized database, we have a tunable consistency model that allows you to give you read predictability and trade-off. You can make the right trade-offs with respect to latency, that you can basically use data locality as a means of building very, very low latency applications, no matter where your users are around the globe. To set this up, here I have a screenshot of the Azure portal. When I create my Azure Cosmos DB account, on the left-hand side navigation, you can see this setting, replicate data globally, and what will be presented to me is a list of regions. We do support geofencing and respect sovereign cloud laws and regulations. And so based off of these policies, a set of regions will be exposed. And what you can do is we offer turnkey global distribution, meaning at the click of a button, just like turning a key in the ignition of your vehicle, suddenly you're up and running. So I click a region. Let's say I select a region in Europe. I'm starting from central U.S. I add a region in Europe. I add a region in Asia and a few other continents. I click on Save, and suddenly my database is up and running. You're no longer spending a week doing database configuration, data center configuration, etc. This is literally something you can set up in a couple seconds. Now, why this makes an impact, like that example from going from West U.S. to Southeast Asia, well, under ideal network conditions, when I ran a test here, if you have your application talking to a database halfway around the world, you're looking at about 200 millisecond latency. And if you want to do something that requires either A, multiple round trips to the database, or B, is latency sensitive, whether that's real-time recommendations, real-time fraud detection, real-time bidding systems, you need to have a very, very low latency profile. Because at the end of the day, if your application is slow and it takes a long time to load, well, the user will hit the back button and say, this is very, very frustrating. By bringing a database replica local to the application instance where the user is, suddenly when I do my load test, what you'll see is I can achieve less than 10 millisecond latency. And so this actually allows you to build very, very robust real-time applications. In addition to the low latency side of the story, coming back to high availability, we do allow you to set up automatic failover. To configure this, you go to replicate data setting and the portal, and then you're going to opt into automatic failover. Today, our model is we have a single write region and multiple read regions. So basically, writes are affinitized to one region, reads are made ubiquitous to all regions. We do have multi-master or multi-write region on our roadmap. But for the interim, what you'll want to do is you want to set a failover policy such that it minimizes the latency impact when you failover. So if I'm going to failover an application, let's say from central U.S. to Southeast Asia, well, the latency characteristics are going to be quite different, right? And so if I have another region, let's say set in West U.S., what I can do is I can do a drag and drop and configure the failover policy according to what my where my user population actually is, to minimize any kind of latency characteristic in the event of a disaster. On top of this, I can also configure my failover policy at an individual client level. If you don't do this, what we'll use is the global policy. However, at an individual client level for your application instances, you might have, and you should have, a set of application instances deployed in each of the regions that you have your database instance. That way, your overall topology is as such. You have a global user base, and they're going to make a request against a traffic manager. The traffic manager is going to understand where that user is and going to be able to route that request to the corresponding application instance closest to it. That application instance is aware of the data center it's placed in and will connect to the database replica closest to it. It's also going to fail over in the event it needs to the closest set of database replicas. In order to configure a different failover policy from each client to or each application instance from region to region, what you can do is, as you initialize the client, we have a ordered list exposed as this property called preferred locations for that connection policy. And what we'll do is we'll always try to connect to the whatever's first in the list, and if that happens to, well, needs to fail over, has trouble connecting, the connection the client is actually smart enough to gracefully fail over to the next corresponding region. All of this is under a single URI. We call this a multi-homing API. And the nice thing is, for failover, you never have to reboot the application instance. The SDK is intelligent. It always keeps a heartbeat and understands the overall global topology, and it'll gracefully fall back to this ordered list of regions as appropriate. You don't need to lift a finger for failover. In addition to automatic failover, we do support manual failover. This is useful if you want to do your own business continuity drills. It is also useful if you find that the current write region isn't actually where the bulk of my write requests are coming from. If I want to actually change and reconfigure what is my designated write region, I can perform a manual failover. And so therefore, you can actually build a model, something like follow the sun, so that if you have a workload that's hot from hours 9 to 5, you can actually choose the write region based off of where the sun is located with respect to the Earth. Basically, follow the daytime, the hours 9 to 5 around the world. Now, whenever you talk about replication, an important thing to understand is consistency. And for this, I'm going to go back to an example. Let's say I have a container with many, many partition sets. And what I'm going to do is I'm going to zoom into that partition set. Furthermore, for this container, I've replicated across 3 different regions: West US, East US, and North Europe. What Cosmos DB does is it actually maintains multiple copies, multiple replicas in each data center region. And this is why we give you the highest availability SLAs in the industry. For even a single region deployment, we can actually financially guarantee 4 nines of availability, meaning that at the end of the day, Microsoft has no interest in constantly having to do SLA refunds. It means our actual availability targets are an order of magnitude even higher than that internally. Now, we give you 4 nines of availability within a single region, and we can give you actually 5 nines of availability across multiple regions. This is made possible by the fact that today we have 4 replicas per region. And so what we do is we can also dynamically tune how we do cross-region replication based off of the consistency model, as well as dynamically based off of the current network conditions around the world. We can do a hub-and-spoke model. We can do a daisy chain of replica sets. This all happens behind the scenes. From a user perspective, what you will have is a set of well-defined consistency models. But what I'll do here is actually give you an understanding of what actually happens behind the scenes and why you care about this. The first thing we're going to do is we're going to have an example where I have a record whose value is 5, and I'm going to update that record from 5 to 6 for that value. Well, it turns out that we obey the laws of physics, and it'll take, on the order of milliseconds for us to propagate that information to these other database regions. So let's talk about a few scenarios. First, let's talk about an unhappy scenario in which we have a network partition. This is the, hey, a natural disaster has occurred or a geopolitical disaster has occurred. What do we do if we lose network connectivity between 2 replica sets? Does this other region continue to serve data, even if it's a stale copy? Let's say it has an old copy that where the value is 5 and it hasn't been updated to 6, meaning it'll prioritize availability, or will it prioritize consistency? And since it's aware that it's lost connectivity to the other replica sets, it'll actually refuse to serve requests. For those of you who are familiar with distributed systems, you understand this and know this as Brewer's cap theorem. And basically, this is an academic theorem that actually proves it's impossible for a distributed data store to simultaneously provide more than 2 out of the following 3 guarantees: consistency, availability, and partition tolerance. Given that this is a distributed system and partition tolerance is a key stakeholder, you're now looking at the trade-off between consistency and availability. And this is a fundamental trade-off where you cannot violate the laws of physics. Now, the thing about cap theorem is it looks at an edge case. And the vast majority of time, while we don't have world wars or natural disasters raining havoc on our world, The vast majority of time, well, all of our data centers are operating in a very, very happy state. That doesn't mean that there's no trade-offs. It takes time to replicate data from region 1 to region number 2. And so you can think of this as I update a record from 5 to 6, and I have concurrent readers in other regions, what is the expected behavior? Do they see stale reads? Do they see the latest copy? In other words, do I prioritize performance or do I prioritize consistency? This is also codified in the academic world in a theorem. People call this pass-elk. And the first 3 letters are given a partition. What is the trade-off with availability versus consistency? This is basically CAP theorem. But what's good about framing it in this context is this is more comprehensive. And so not only is there a trade-off, given a network partition, what is trade-off between availability versus consistency, else in the common case scenario, what is the trade-off between latency versus consistency? This is why you care about these consistency models. And what I found is when I look across all of the distributed databases on the market, most of them actually bucket you into 2 categories and force you into these extremes. Either they claim, you know what you want is strong consistency, but what they don't tell you is, well, we still have to obey the laws of physics, and so you are going to pay a very, very real performance penalty in the form of latency. Or some of these other database systems will give you eventual consistency in which you have a complete lack of predictability in building the application, but this comes out of very, very nice performance benefits in which you get low latency characteristics. And the thing is that there are actually very real-world scenarios for both of these different consistency models. At Cosmos DB, we don't believe in forcing you into these extremes of black and white. We give you some nice shades of gray in between. And so we've worked with many academics at different universities where something like 60 different consistency models have been proposed over the years. And what we've done is we've taken a very pragmatic approach of selecting 3 additional intermediate click stops for you to tune and navigate this trade-off that have very, very real, meaningful, real-world scenarios so that you can actually navigate and choose the right trade-offs between latency, availability, and throughput for your application. We also make this very easy. You don't have to deal with write concerns or quorum configurations. Instead, what we do is we have them nice, easy, click button in the Azure portal. You click on which consistency you want, and you're done. So let's talk a little bit about the different consistency models. We support from left to right, left side being the strongest consistency, right side having the lowest latency and highest availability characteristics, as well as the best throughput characteristics because we don't have to do quorum reads. From left to right, the consistency models are as such: strong, bounded staleness, session, consistent, prefix, and eventual. Now, strong consistency is, I think, what's well understood. Basically, we guarantee this concept called linearizability, meaning that when you complete a write operation, it's immediately made visible to all subsequent read and write operations. You'll never see a stale read. And there's a set of scenarios, like let's say you're doing order transaction processing in a manner that you're updating the state of an order. Well, in this case, you might not want to relax consistency because you want to avoid accidentally charging an order twice or multiple times for payment. If you do that, your downstream customers they might not be very happy because you took an order that was still being processed, you charge it for payment, you persist that back into the database, and then you end up accidentally reading a stale record, a stale copy, and reprocessing the same order again. In contrast, let's go to the other end of the spectrum. Let's say I'm building a social media application like Facebook. If I have billions of users around the world, I really don't want to have a very slow-loading website that takes many, many seconds to load just because a few other billion users have liked some other post. Instead, I want this to be a very low-latency, fast-loading web experience. And so I might relax consistency all the way to eventual, because you know what? If I go to my friend, let's say I have my friend Anita liking a newsfeed post, well, I'm okay with seeing her like, a split second later. I don't care if I get a stale read. What's more important for me is that the page loaded fast. But the thing is, for eventual consistency, you have a complete absence of guarantees. So let's take a look at the intermediate click stops. Let's look at consistent prefix. Rather than replicating data on an operation per operation basis, let's say I'm building a messaging application for a group chat. And in this group chat, I have Alice and Bob organizing dinner and saying, hey, what time should we go to dinner? How's 7 o'clock? Oh, I'm busy. How about 8 o'clock? Oh, that sounds perfect. Great, let's meet then. Carol and Dan are also part of this group chat, and if they see these messages out of order, because at the end of the day, when we send out network packets, they can arrive in any order. Some people see, 8 o'clock, no 7 o'clock. Some people see 7 o'clock, no 8 o'clock. Well, Dan and Carol are going to be very confused when one of them arrives and the other is not there. Meanwhile, the other arrives late and sees that everyone's already finished dinner, and he's going, hey, what happened here? And so what consistent prefix does is we guarantee that we always replicate off of an underlying log. We are a log-structured store, and we guarantee that all of these operations are replicated in order. You'll never see out-of-order updates. You'll never see gaps in time. And so if you send messages 1, 2, 3, 4, 5, if you see 5, you're guaranteed to see 1 through 4 in order. If you see 3, you're guaranteed to see 1 and 2 in order. We can further strengthen this consistency, and for that social media example, session consistency is typically the sweet spot. Basically, I don't need a global strong consistency. I don't really care about the other billions of users liking posts, but what I do care about is when I post a comment and I refresh that page, I see my own comment. Because if I don't see my own comment and I get a stale database read, well, I'm going to be confused, and I'm going to go, oh, maybe the application didn't accept my comment, and so therefore I'm going to post that comment again. And pretty soon I've posted it 3 times. I get frustrated because I keep getting stale reads, and then I give up. Meanwhile, my friend Anita's watching my Facebook, and I keep saying the same thing over and over again. And she's going, what is wrong with Andrew? Like, why does he keep saying the same thing over and over? Is he just kind of weird? So session consistency, actually, what we can do is we can scope strong consistency down to a single session. Within that session, you get actually reads follow your own rights. Meanwhile, you don't have to pay the performance penalty for a global strong consistency. This is actually the sweet spot for the vast majority of applications. And when we look at telemetry, this is the most popular of the consistency models. Lastly, we'll talk about bounded staleness. Bounded staleness gives you a SLA on how eventual is eventual. Because at the end of the day, eventual might mean anything. It might mean, a millennium from now. It's still eventual because there's no guarantee. Anyone can do that. So bounded staleness, what we do is we actually allow you to set a bound in terms of how many seconds or how many minutes. So a duration of time, as well as a number of operations. Think of this as a staleness window, and it's a sliding window. All operations outside of this window, we guarantee strong consistency. And what we'll do is we'll actually prioritize replication over other processes in order to meet these SLAs. Now you have a very, very tight bound on how eventual is eventual. The only possible stale read is within that staleness window, and even then we guarantee a consistent prefix. So selecting these in the Azure portal is very easy. It's a click button, turnkey solution. For bounded staleness, we just ask you for 2 dimensions, the number of operations as well as the amount of time for the maximum staleness window. For session consistency, we maintain that session through the concept of a session token. By default, the client SDKs will cache these session tokens on your behalf. But if you have many, many stateless application instances, what you'll do is every time you perform a write application, you'll pass the latest session token down to that user, maybe in the form of a cookie file, and then when they make follow-up requests, they'll supply that value back into the application instance and override that read request with that session token so that we can pin that user to that session token and guarantee that they're reading their own writes. We can also relax consistency on a per request basis. This is easily done by just tuning the request options for our requests in our SDKs. And then lastly, I'm going to give you a brief overview of indexing, and then we'll jump into questions. For indexing, one of the neat novel features that Cosmos DB has is automatic indexing. And so you can store a heterogeneous set of records. Let's say it's IoT data where each generation of device has slightly different sensors and new capabilities. What we can do is we can automatically index every property of every record without knowing the schema up front. You never have to do an alter tables or create index operation. This is made possible by the fact that we use an inverted index. Those of you who have played with information retrieval systems in the past may be familiarized with the concept of an inverted index. And what we have done is we have built a latch-free, write-optimized data structure to bring this over to the world of databases. Here in this example, I have two different records, and I'm going to use the document-oriented data model just for sake of example. Notice that these two records have two different schemas. On the record on the left, I have some exports where I just have a city property. On the record on the right, I have a set of exports where I also have, on some of these cities, a set of dealers. Well, what we do is, behind the scenes, what our index looks like is, first we'll model these records as trees. And this is our atom record sequence data model. Our proprietary data model that we can actually efficiently project for all of the data models we make available. We build a tree representation where the root node is the document ID or the record ID, and each of the properties underneath become child nodes. The instance values become the leaf nodes, and the nice thing here is I have two drastically looking different trees. Because I have two different schemas for these two different records. Basically, we're going to now have a schema at a record level. Schema never goes away. It's still defined at a record level rather than at a, let's say, a table level. Now, what the index looks like is we can basically combine all of these trees and establish pointers to the actual underlying set of records for a query result. And so if I combine these inverted indices, or these trees into an inverted index, I have a tree that looks as follows. And now let's navigate down the left-hand side of that tree. Let's say I run a query where select star from this collection where the first location's country is Germany. What we'll find is Germany actually has a pointer to record ID 1 and 2. And so therefore, I can efficiently return records 1 and 2 in the query result set. Meanwhile, if I go to the right-hand side, down that path dealer's name, who's Hans, that was a unique property for that particular record. I can still do something like select star from this collection where the first export's dealer is Hans. And what I'll find is that only has a pointer to record number 2, and therefore that's what I'll surface in the query result. The nice thing about data is 90% of the paths or properties in your records will have a high degree of commonality. And so we can get away with automatically indexing every property of every record while still compressing this to a point due to how many common terms you have, such that the storage overhead is very, very minimal. We do give you also options to tune the automatic indexing. And at a high level, the important things to understand is you can have a set of included paths as well as a set of excluded paths. And so by default, we include the path /star, meaning we'll index everything. Now, the more specific the path is, we'll override entries with less specific paths. So you can always include /star and exclude, a set of paths that you never have to query on, or that's an opt-out approach. Or if you want to go back to a traditional approach, you can set only a whitelisted set of included paths. This gives you a pretty good comprehensive view in terms of at least a technical crash course over Cosmos DB in terms of the resource model, how we do resource governance, partitioning, replication, and indexing. Now I'd like to open this up to Q&A. For those of you still on here, I realize we're a little bit over time, so I'll just take a few Q&A and we'll do our best to get back to you. And I'll take the first three questions I see. So question here is data copied one-to-one for geo-replicating? Well, what we do is we tune our geo-replication at the account level. And so at an account level, all of the regions that you specified will have the exact same copy of data. We do have design patterns for deploying a data access layer across multiple accounts so that you can basically have a set of partition data with different geographic configurations. But otherwise, we replicate everything under the storage account. Next question is, how do EU GDPR laws apply to Cosmos DB? And for us, we are a GDPR compliant data store. And when you delete records, the main important thing to know about GDPR is there is a right to be forgotten, and from a user privacy point of view. And what that means is that when you delete records, you must be able to prove that you've deleted that record within, right now I think it's still ambiguous on the time duration, but you need a data store that basically supports delete and is not an append-only system. Cosmos DB is a GDPR compliant data store. We do support both. You can easily tag and use our automatic indexing to tag entries, to easily query off of those, and then to do hard forced deletes across all of those records to be GDPR compliant. The automatic indexing actually gives you a very, very convenient way of approaching this problem. But at the end of the day, this is a shared set of responsibility. We can ensure that the data store itself is GDPR compliant. From an application development standpoint, you still need to be mindful and making sure that when a user asks to be forgotten, you actually do the queries and delete the relevant entries in the data store. Another question is, can you write operation on multiple replicas? So today, our model is writes are affinitized to a single region, reads are made ubiquitous to all regions. You can dynamically configure the right region through manual failover. We do have multi-write regions as part of our roadmap. We also have a set of design patterns that you can take advantage of today, where the gist is you're basically going to have a data access layer abstracting over multiple accounts, where writes continue to follow the model of they're affinitized to one region, but can be a set of regions, and reads made ubiquitous to all regions. Do feel to reach out with us. We've seen a lot of these applications deployed, and we'd be happy to help you design that solution. With that said, we thank you for watching our webinar. To learn more about Azure Cosmos DB, please visit our website at www.azurecosmosdb.com. We do have a few free trial experiences. You can sign up for a free trial on Azure at aka.ms/Azure account. We also have a pool of Cosmos DB databases that we can give you a temporary release for free. In other words, you can try Azure Cosmos DB for free at aka.ms/try-Azure-Cosmos-DB. And this is a weekly webinar series. Please join us next week to learn more about AI and serverless technologies. Thank you very much for joining us. Hey, for those of you who are still on the line, I do realize there's a lot of Q&A here. So what I'll do is I'm going to actually go down the list a bit more and answer a few more in case you are interested. So going down our list, the next question is, what are all the actions that cause request units in Cosmos DB? This will be any user issued request. We do have a set of background requests where we eat the cost of, but anytime a user makes a request, at the end of the day, this is going to use up CPU, memory, and I/O. It uses physical resources. There's no such thing as a request that doesn't use physical resources, and so all user issued requests will have a corresponding request unit charge. The next question is, for read and write operations, is request units calculated measured by partition, or is it the total cost across all partitions? This actually depends on the nature of the operation. Basically, come back to understanding what an RU is. It is the CPU, memory, and I/O footprint of a request. If your request spans a single partition, then what will happen is we'll deduct the RU from that particular partition. We do evenly distribute the RUs across the underlying partition sets. And this is why we also ask you to load balance your requests evenly across a set of partition keys. If you do have a request that requires a fan out, it'll be the corresponding physical load on each of the underlying partition sets. For fan-out requests, I mean, the main request that you're going to be looking at here is queries. And for queries, it's what we found, at least at this point in time on our current topology, typically is dominated by the amount of I/O. So if you hit a partition that doesn't have relevant data, the footprint is actually fairly minimal in terms of RUs. However, if you hit a partition that actually has meaningful query results to be returned, it's going to do a bit more I/O, and therefore, for that particular partition, it's going to use up a little bit more RUs. Question is, what about encryption? How is data encrypted? We encrypt data both at rest as well as in transit. For encryption at rest, we just encrypt all data stored. It's actually a default option. We don't believe in not encrypting data. We don't want to carry the liability of storing unencrypted data. And so we just encrypt everything. This happens by default, and we eat the cost for this. We pass it on for free. We're not like some other cloud vendors that actually charge you with hidden costs on encryption at rest. Like, ours is free. Furthermore, on top of encryption at rest, in which we use AES, we also encrypt all data in transit. We also enforce this. We won't allow you to establish a connection to the database on an unencrypted line. And we enforce TLS 1.2 or SSL for all connections made to Cosmos DB. I'll do two more questions. Can partition keys be compound keys, or are they one value? If compound is possible, is it best practice to have it be one value for scalability? We don't support compound keys out of the box, but we do advocate for using compound key. The common technique I actually see a lot of people use is they'll annotate their records with an artificial property called partition key. This is for two reasons. Number one is this is how you can form a compound key. Basically, what you're going to do is you're just going to coalesce, or not coalesce. You're going to just append multiple attribute values together to form that partition key and populate that in that partition key value on that record. So that is your mechanism for forming a compound key. The other reason for setting an artificial property like partition key as your partition key is this also allows you to dynamically change this after the fact. Because at the end of the day, once you choose a path, we stick to that. That choice of what is your partition key path is immutable. We don't allow you to change this because this means reshuffling and redistributing all of the data on all of the different storage partition nodes. But with that said, If this is, let's say, a telemetry store where you're only having a window of time and you want to late bind and change the partition key by forming a composite after some time, well, what you can do is you can just change how you populate new records. And because you're aware of what the old way of populating and the new way of populating, you also know how to query over that data set. Last question, is a partition key like a sort of routing directive? A partition key both controls distribution of data as well as routing of requests. You should think of it actually from both dimensions. Thank you for sticking around. If you have any other further questions that we haven't addressed, please engage us over Twitter. We do actively monitor our Cosmos DB hashtag, as well as feel free to send us a mail. We're highly responsive about that as well. Thank you very much.